Hello, and whoops, I forgot to prop up my webcam. There we go. Welcome back to Advent of Code 2018, day 23. It's Christmas Eve. And we're almost done with this, and December's coming up. The real December's coming up in a couple of days. Okay, so let's crack on then. Whoops, hang on. Oh, this issue again. Hang on. Something. Every time I. Desktop audio. There we go. No, that didn't solve it. Desktop audio. Speakers. Alright, okay. Day 23. Experimental emergency teleportation. Let me change which lights are on. That light is... That's better. Using your torch to search the darkness of the rocky cavern, you finally locate the man's friend, a small reindeer. You're not sure how I got so far in this cave. It looks sick. Too sick to walk, and too heavy for you to carry all the way back. Sleighs won't be invented for another 1,500 years, of course. The only option is experimental emergency teleportation. You hit the experimental emergency teleportation button on the device and push I accept the risk on no fewer than 18 different warning messages. Immediately, the device deploys hundreds of tiny nanobots, which fly around the cavern, apparently assembling themselves into a very specific formation. The device lists the XYZ position, pos, for each nanobot, as well as its signal radius, R, on its tiny screen. Okay. Each nanobot can transmit signals to any integer coordinate which is a distance away from it, less than or equal to its signal radius. Less than or equal to, okay. In range of that nanobot. Fine. To determine which nanobot is the strongest, which is the largest signal radius, and then for that nanobot, the total number of nanobots that are in range of it, including itself. That's easy. You just go through each nanobot one by one and work out the Manhattan distance, which is just x plus absolute value of x, absolute value of delta x plus absolute value of delta y. Hello, Zen. Nanobot was scary. Yes. I think part 2 is going to be tougher because Amara said something about this. In range of its. So when they say in range. Total number of nanobots that are in range of it. So they mean that when they say in range of it, they mean that this nanobot is able to transmit to them, but not necessarily the other way around, I assume. Well, DIJ sent will deliver the presents directly into your blood. Yes. Is that what they mean? Yeah. I'd argue this is slightly ambiguous. This sent. Okay. Okay, no, it's not. It's not ambiguous, but it's slightly ambiguous. Okay, anyway, but I think I get what they mean. Right, so yeah, because they're not checking the R values for any of the other nanobots. So we're finding that. Okay, fine. This is an easy part 1, unless I'm missing something here. How many do we have? Not that many. Okay. Yeah, you literally just go through the whole list and check, do the, do the distance check. Alright, so that's, okay, so we've got to parse this first. Oh, I don't like parsing stuff like this. Should we be a bit naughty? Should we use the Python's exec function? How do I do that? Those are some big radius numbers. Yeah, I have a feeling part 2 is going to do something a bit trickier, but part 1, it seems it doesn't matter how big the numbers are, we just have to compute the distance, I guess. Okay, so I'm going to use the Python's exec, so that will treat this line as code and execute it. The only problem is that symbol there is not what Python would recognize. We would need it to be that. But we can replace. Hang on, how do I do this? So we want to just copy some code from before, this line here. Okay, full line. We want to put the nanobots into this list. Actually, no, let's call it pause list and R list for the radii. So we want let's do line dot strip, and then we want to do dot replace the angles with that dot replace that with that, and then I also want to replace that comma space with a semicolon. Can you use a semicolon this way? Dot replace. These indicators are taking up too much space. So I'm going to replace that with semicolon. I'm not sure if that's valid. We'll try it and see. So we want exec and now just execute that as if it was code. So this is kind of a very slow thing to do. You shouldn't really do it when you're writing Python programs, because you're actually spinning up code instead of just parsing something like... But it'll work, I think. What do we want to do? We want to put... pause list dot append pause r list dot append r. You're replacing yes, that's what I want. I want it to look like... Ooh. Damn it, why does it do that? That. Did I do it right? So that the right hand one should be that one, right? Yeah. Right, let me try running it now. Oh. Pause and R have got to exist. Okay. Let's have a look. Print R list. Nice. That's something that you can do in Python that actually helps in a lot of advent of code. I mean, that was only minor, but there's been cases where it made all the difference, and anyone who used Python had access to exec. I think JavaScript also has something similar that can do stuff like that. So Python and JavaScript users were able to solve certain problems with ease, while those poor C++ users were having to write their own parsers. Yeah, it's really useful. I mean, you never actually use exec in real Python programming because it's an incredibly slow process, because it's actually spinning up Python code in order to execute that one line when you could just extract the numbers. But yeah, it's cheaty and it works. All right, so now what? We want to find the largest signal radius. Max R equals max of R list. Okay, let's make a little helper method here. Define distance from U to V. And this is going to be the Manhattan metric, so it's going to be return absolute value of the first parameter minus the first parameter of V plus absolute value of U1 plus absolute value of U2 minus V2. So this we can do this in one line basically. Just count equals sum of no, we need to know which was the max. Because we need to know its coordinates. So we need there was a way to do this in Python easily without having to write a me do this again. Argmax is what I'm trying to do. Let me Google this. Python argmax. Argmax returns the item that was mac. The item that was... No. What am I trying to... Ah, yeah, no, I know what I mean. I want to do this. We want max r equals max I... So we're trying to find the index which provides the maximum radius. So we're trying to maximize that quantity there, r list I, but we want to know the index. We don't want to know the value. Let's call it max v. No, max I is an index. Okay, so nanobot equals pos list max I. Radius equals r list max I. So now we want to we want to count the truth values, sum up the truth values, which is basically the same as counting of this boolean here. We want to say if, so we want the dist of v from the nanobot is less than or equal to the radius for v in pos list try that 780 that's it, that's part one. Correct. That was a very easy part one. That could have been like a part one for one of the first few days. Alright, well, part two is probably going to be harder. Now you just need to figure out where to position yourself so that you're actually teleported when the nanobots activate. To increase the probability of success, you need to find the coordinate which puts you in range of the largest number of nanobots If there are multiple, choose one closest to your position. Huh. So we want to find the coordinate which lies in the maximum number of these disks. This could be tricky. Because the numbers are big. But let's think. So you don't need to try all individual grid coordinates. In fact, you can just try the edges, because if you think about it, oh wait, let me continue what I was saying there. So the brute force way would be to try all the coordinates in some gigantic rectangle around these nanobots. Try every individual location. The less brute forcey way, but still might take a long time, is to just try the edges of these discs instead of all the what's inside the discs. So these nanobots have a disc of radius r around them. So instead of trying every element of that disc, just try the edges, because you might as well. Because if two discs intersect, or if a whole bunch of discs intersect, then you can move a little bit left or right until you're on the edge of one of them and still be in all those discs. So you might as well just take the edge points. So that massively decreases the number of locations we need to check. Just for each disk, we just check the boundaries of it and count how many disks. That still might take too long, so we still need to cut it down somehow. So that goes from... So if the radius is r, instead of checking r squared, we're now checking like r values. That's a huge decrease. Let's have a look at these numbers. So R is almost 1 billion. That's still a lot. That's still too much to check. Fine. How do we improve on that? There's definitely been a similar problem in the past. I'm trying to remember what I did for that. Do we just need to check the corners? So, okay, so these discs, I say disc, but really they're like diamond shapes, rhombus shapes. Do I just need to check the 4 corners? Because if two rhombus, what's the plural of rhombus? Rhombi? Rhombi or rhombuses. Okay. Two rhombi intersect. It's necessary that one of the corners of one of them will be part of that intersection. One of the 4 corners must be part of that intersection. I think I need to whip out Microsoft Paint for this. Hello, Amaro. I'm on problem 23. I just did part 1, which was just extremely easy. That could have been like a first 5 days problem. I'm now on part 2, which is clearly harder. Just whipping out Paint so I can explain things. Okay. Okay, is there a dark mode for paint? Because this is quite bright now. Oh yeah, there is. There we go. Okay, so what am I saying? So, okay, so you got rhombuses, rhombi. Some are small radius, some are big radius, and they intersect sometimes. So we're trying to find the area of maximum intersection. Now, I think wherever that area is, I think it's gonna have to be one of the four corners of one of these rhombuses. Is that true? Could it not be the case? I dare you to draw a perfect circle with a mouse. This was also controversial because a lot of people use an SMT solver. SMT solver. What's an SMT solver? There's my perfect circle. I can see how it'd be like Z3. Oh, what does SMT stand for again? That's a decent circle. Because I can see how it's like a linear program. And there are linear program solvers out there. No, it's not a linear program. Is it? Yeah, it is a linear program. Well, not really. But it's similar to a linear program. Satisfiability modulo theory solver. Okay. I mean, I think that's fair game. It's not... It's no different to using a calculator, to be honest. I mean, the hard bit is translating the problem into the language of the solver. I think it's fine if people use the solver once they've kind of worked out the theory of it and entered the input into it. It doesn't seem like cheating or anything to me. Say a circle and you make it 2, also that close intact. There you go. Oh, even doing this... Okay. Is there a way I can make this fixed? Only I don't want it to be an oval, I want it to be a circle. Oh well. Oh, this is useful. Hang on. I could have used this. This is perfect. We want them to be regular, though. Alright, so my claim is that no matter how many rhombuses you have here, wherever the maximum intersection is, one of the four corners of one of the rhombus will be in that intersection. So it suffices to just... Hold on, now you're very beginning with this editing. It's so basic, MS Paint. MS Paint is brilliant. Like, what more do you need? Unless you are actually using any advanced features of Photoshop or whatever. Microsoft Paint boots up so much faster. There's no lag. It's a brilliant piece of software. One of the greatest pieces of software ever made. Photoshop, you have to wait several minutes for it to boot up, and then it's pretty heavy on the graphics and everything, but... So I'm trying to claim that one of the corners is always inside the intersection. Is that, how do I prove that? Is that true? Can I make it so that it's not true? It's not true. Look, I just made one where it's not true. So this area here is the maximal intersection. So okay, you're not looking at the corners, but we can look at the intersection points between these rhombuses, because how many of them are there? Killing my boring time string where I draw a lot of unsymmetrically Batman. Okay. Okay, so if a rhombus intersects another rhombus, it could create like two intersection points with that rhombus. So if every rhombus intersected every other rhombus, which is not the case and probably not even possible, then there's 1,000 rhombuses. So that's like 1 million. We've got millions of intersection points. We can check millions, that's fine. But for each of those millions, we want to check. So for each intersection point, we want to check whether it's how many rhombuses it lies in, right? Will this work? Okay, so what I'm saying is I just I locate all the points. So all these crossover points across all the rhombuses. So you can do that just by checking pairwise. Which will take a million operations. We can manage that. And then for each of them, I just check how many rhombuses it lies in, but that would cost 1,000 operations. That might be too much. Then we're working with the billions. But there might not be as many intersection points. There might not actually be that many. I don't know. Why don't we find out? Okay, so so this would work, right? That will tell us the maximal intersection area, but then we're not done. We need to find the point which is closest to the origin. So there might be several different areas. We have to choose the one which is close to the origin. And okay. Is there a better way of doing this? Um, the thing is, what do I actually mean by intersection point? The lines are actually, no, let me, are grid coordinates, right? I can't really. Okay, get rid of all this. I just want a normal, okay, brush, fine. Okay, so a line, just bigger. Okay, so a line is actually a bunch of points, right? Like this. So when two lines intersect, either they intersect on a point, so if this line is intersecting this line, they would intersect here, at that point there. Or they would actually cross over like this, I guess. In which case, what do I actually want from that? I guess if this is one rhombus, and this is the shaded area, and this is the other rhombus, and this is the shaded area, I would want just to take like I'm not sure whether there's even a problem here. I don't think there is, but just trying to think how exactly I'm supposed to code this. This one can't be brute forced, it would take like a year to finish. Oh yeah, I'm not brute forcing it. Brute force would be to try every pixel in the XYZ plane. I'm just reducing it to trying every intersection point, which is it's quadratic though, but can I cut it down further? Take like a This situation here is confusing me a bit. I'm trying to think which pixel I want now, because this is the coordinate I want for the intersection point of these two. Here, I guess I just want arbitrarily one of them, but not this one, because that is outside this rhombus. So I want this one because this one and this one and this one lie. Oh no, this one. This one's actually outside. So either we take this one or this one to be our intersection. What's the question? So I'm trying to find the intersection points between all the lines. Because once I have that, then I just need to check all those intersection points to see, instead of checking all points in the plane, I can just reduce to just checking each of those points and counting how many diamonds it lies inside. So for each, there's just a confusing situation because they cross over in two different ways. Two lines intersect either like this on the right. Wait, have I got my mouse enabled? Yeah, I do. Two lines cross over either like this, or they cross over like this. This is the one on the right is the nice one because there's one pixel that is common to both lines, which is exactly what I want. The one on the left is a bit weird because there's 4 pixels in the middle there. And 2 of them are invalid because they don't actually lie in the intersection. They actually lie outside the other rhombus. The 2 at the bottom are the correct ones we want. And either one we can use. Okay. As long as we keep that in mind, that's how I've got to code it. Binary search or an octree, maybe. Or what? Binary search, I don't think you could use binary search here, because no matter how you divide the space, you don't know whether the maximal intersection is in one half or the other. You don't have anything to rule it out, do you? Okay, so maybe I just consider all four pixels here, because there's no harm in actually using these other 2. It's just they're not actually in the intersection. So maybe I just add all 4 of them to the list. So for every pair of lines, we work out whether they intersect, and we add either this pixel to the list or we add these 4 in the middle to the list. So we have a list of all intersection points, which could be quadratic, which is still quite a lot. And we know that wherever the maximal crossover is, one of those points must be inside it. Because you can't have a situation where one of them isn't. When you're in the maximal intersection, you can keep going left or right or up and down. Eventually, you'll hit an edge, or get to a corner, and that corner will be one of these points, right? So is that it then? Do I just do that? The only problem is there could be a billion of these points. Let's just find out, I guess. Okay. So what do we do here? We want to create a list of lines. So a line is defined by 2 points on the line. And that means all the other points between those two are also on the line. So we want a list of lines. So we got lines equals list. For I in range length. Or let's say for I pause in rate pause list R equals, so we've got the radius. So this gives us one rhombus with its center and its radius. And we want to know all 4 line segments. So corners, we need to find the corners. So corners equals, so it's going to be, so the top will be oh wait, we're in 3D, not 2D. Oh fuck. I'd be working in 2D, but the same, okay, so most of what I said kind of holds, but maybe not quite as well. Oh damn, yeah. Wait, no. Some of what I said doesn't hold. The whole edges thing doesn't hold. Whoops. Okay. It was hard enough in 2D, so we're in 3D. So these basically look like 3D diamonds. Which are overlapping. So when 2 rhombuses intersect, we've got intersection points on their boundaries. When 2 3D rhombuses intersect, you have a whole line of points where they intersect, which is more complicated. All right, maybe I gotta take a step back and go back to the thing about corners, because it'd be nice if we could just check all the corners. Oh man, I'm not really sure what I want to do here. But it's wrong. You can't just check the corners, because you can have rhombuses intersect a way such that none of their corners are actually in that intersection. They're just intersecting along their flat surfaces. So... Oh man. What if we get lucky? What if it just happens to be the case that one of the corners is in the intersection? That would make things easier, wouldn't it? They're all very big radii. So I wonder if... Let's try the corners approach. I don't think it's... You can try to visualize it. Well, that's what I was doing with Microsoft Paint. I don't think this is actually completely mathematically correct, because the... So I reckon that if we're lucky, one of the corners will be in that intersection. And then that would suffice to check all the corners. But it's not necessarily the case, but it's very likely to be the case. Like, divide by 10 million rounded up and print the whole thing in code to see zeros and ones. What do you mean? To see zeros and ones. This is 3D though. It's not 2D. I would need to print them in a 3D program or something, which can be done. There's only 1,000. That's actually not that many. We could actually just use a 3D program to put all these shapes in. Alright, let's just try something. I'm gonna try the corners approach. I don't know if this is correct, but we'll just do it. Alright, corners equals. So it's gonna be... So it'll be... pos 0 plus r, and then just pos 1 and pos 2, is that right? So if a have radius 1, one item or one element away. Yeah. That's one corner. How many corners are there? And then we need to do this. Oh, there's a... I think I'd try an octree scan first. I mean, I think I know the proper approach for this, the correct approach, because this is computational geometry. You normally use a trapezium map. You every time these two polygons intersect, you divide them up into trapeziums instead of these gigantic shapes. So then you split up the whole thing into these trapeziums, and then it's very easy to work with because these are convex shapes. So you just break everything down into small pieces, and then you just have to check those pieces. And there'll be millions of thousands of them, but not many. So that'd be. But to code that would be a bit. You'd need to do lots of geometry then. But that's like the proper way to do it. That's what libraries do when you. That's what you do in game programming as well. The libraries are computing the intersections between convex shapes. That's why you have colliders always, which are like cylinders or spheres and rectangles, because it's easy to detect the intersections. But if a person's body is made up of head and arms, then you need to split them up into convex shapes and then compute the intersections of those convex shapes. So can't see part 2 on my end. Part 2 is saying you need to find the coordinate which puts you in range of the largest number of nanobots, but you also have to choose the one which is closest to 000 if there's a tie. So yeah, basically these nanobots disks are all intersecting, and you need to find the coordinate which is inside the most of them. There was a problem which was pretty much exactly this in the past, and that was completely 2D. So this is a 3D one now. Actually, no, that problem was a newer problem. I think it was last year's or the year before. Oh, I think it might be last year's. Yeah, that was just 2D, so this is actually harder. Okay, so corners. All right, let's just say deltas equals. So it's going to be R0, 0 minus R0, 0. Then it could work to divide everything by million to make runtime faster. By million. If the intersecting space is quite large, then yeah, that might actually work. I don't know. So if I were to do that, just divide all the radii by million. So it'd be like I is 64, I is 62, and so on. Then then we can solve it with brute force and just see what we get. It's worth a try. Let's try that then. Otherwise I'll go back to this corners thing. I'm not sure that the corners thing is correct though. It's just wishful thinking. Corner, there may not be any corner in that intersection, that's the problem. It's just guessing. Alright, so R smaller equals R divided by million for R in R list. And now we just solve it by brute force, basically. We say, for so what do I want to do? Just go through each of the... Okay, for... So for each pause, well, we want... For each pause, we basically want all the points. Or just all the points on its boundary. How do we get that? Shall I make a helper method here? Boundary of a for a given index. How do you get the boundary of one of these diamonds? You're given a radius and a center. You basically want all the points which are maximum. So, fixed distance of R from that point. How do you do that? You want... You want to split R into 3 components, basically. Okay, I think I know how you do this. You do for I, for, let's say, K in range R. for j in range, we start from so it's going to be r plus 1 minus k. And L will be r plus 1 minus k minus j. So basically I'm forcing k plus j plus L equals r, but I'm trying all possible values of k, j, and L such that that's true. So k can be anything from 0 to r included. J can be anything from 0 to r plus 1 minus k. And L is whatever's left over, so that will force these to sum to... We don't need the 1 here. Okay. Now that I've got those, I basically say... bpos, boundary pos, equals... It's going to be pos 0 plus... wait, there could be negative as well. We need to have all positives and negatives, so... Some people solved it by converting to 4D coordinates. Quaternions. I haven't worked with quaternions much. I know they get used a lot, but I don't know what you would actually do with them. Oh, okay. We need more for loops here. So we've got K, J, and L, but now we have to choose the signs. So for sign 1, so we need, for S1, this is a sign in -1, 1. For S2 in -1, 1. For S3 in -1, 1. Yield, so that it's going to be pos 0 plus k, pos 1 plus plus S1 times k, pos 1 plus S2 times j, pos 2 plus S3 times L. So that should get the whole boundary. Let's test it out. Print x or z. I'm not using x by z because it will be like the coordinates. Let's just say w for w in get boundary. Just say the first one. No, stop. We want to use what is pos here? Whoops, I haven't said what pos is, so it was just doing that for loop. Alright, So pos equals pos list I, radius equals, we want to use the small one. There we go. So it's printing the boundary. Does that look right? Two oh two one five eight, 202.160. And that's for first one, which is, so we divide that by millions, so we end up with radius like 59. We actually rounded down. So I will assume it's correct. I don't know. Now what? We know what the boundary is, we just have to check all of those points, so... So the candidates... Basically, we take every pair of disks, get their boundaries, intersect the boundaries. That gives us a set of points which are on both. Those are our candidate points. If we just check every candidate point, then that's all we need to check. We don't need to check all boundaries because we could just reduce it further. Let's try this then. Okay. For I in range and pos list. J in range and pos list. If I is J, then we can continue. So we want boundary 1. So intersect equals set of get boundary I union no intersect, which is and set of get boundary J. So intersect the two. So ultimately we want candidates equals empty set. And now we put these in the candidates. So now, once we've done that, should be 1 million operations or so. Because we're doing every pair. That's 1,000 times 1,000. Alright, so print candidates. There we go. No, it's still running because that was this. No, it'll take a while. But no, shouldn't take too long. Actually, no, it will take quite a long time. Because it's million times the size of these boundaries. Also, I'm recomputing these every time. I shouldn't have to do that. Okay. There's a faster way to do this. Let's say boundaries equals set get boundary I in range. What's this? I should just have n. N equals length. What's this? Alright, so we've got a bunch of boundaries which are all computed. Let's see how long it takes to do that. Might still take a while. Spelled it wrong as well. Okay, so now it's gonna be 1,000 times whatever the size of these are, but it's. I mean, these sizes are divided by. Oh, whoa, 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 we're using the wrong. We're not using R smaller. It's doing it with the big set. No. It is using the small set. Get boundary. So it should only be up to like 100. Radius is 100, so then we should only have a few hundred points, right? Oh, no, because there's actually quite a lot of points in the boundary. Man, this is so messy. Okay, so it takes too long to compute all these boundaries. Oh, okay, well, I mean, we can just reduce by more than 1 million, 10 million now. The tiny little shapes. Will this still work? Okay. So now we've got a whole bunch of boundaries. Okay. And now intersect equals, it's going to be, now we don't have to compute the boundaries multiple times, it's just boundaries I and boundaries J. Alright, so we're computing the boundaries, and now we're just kind of put this here as easier. This problem is pretty hard, but I've been, well, actually, yeah, there were some hard problems for 2018. If you, yeah, the assembly codes were quite hard. Still, I think there was some recent years did have some harder problems overall. Empty set. Am I not using this notation correctly? How do I? You know what? The thing is, boundaries don't actually need to intersect. They could cross over each other, like I did in that diagram. Because we're not working with perfect floating point lines. We're working with pixels. But that's not the reason why we got the empty set. I think, is this notation right? It's if intersect print intersect. There's no intersections between any of these boundaries. What? Oh, of course. Of course there isn't. Because I didn't scale down the integers too. So they're all just tiny little radius, but they're still in their respective positions. That's... Whoops. Okay, instead of doing this, scale everything down. From the beginning. So we want to use our list. Where do we... It's going to be pause divided by scale. Oh, how do I do this? Tuple W divided by scale for W in pause. Scale is 10 million for now. Let's try and get it to do something. Alright, now we've got intersections. Alright, stop printing those. This is the candidates. Okay, fine. So, I mean, this will scale down, so it might now be wrong. But we've now got a list of candidates. Print the length of candidates. I just want to see how many we've got. Got 8,000. All right. So if this was completely... If this wasn't scaled down, this would be correct so far. No, because what I said, you can have two boundaries crossing over without creating an intersection. It's a bit weird geometrically. I don't know how we fix that, but whatever. Just work with this. We're estimating at this point. Now what? For each of these candidates, okay. For P in candidates, we want to count. So best P equals none. Best let's say just discs is 0 or 1. Okay, so for P, oh no, 2, because these are intersections, so... No, just stick with 1. Right, for P in candidates, so now, for each of these points, go through all the disks. So we want to so the number of disks that this point lies in equals, we just copy something we did earlier, this, roughly, equals, so it's going to be distance of our point to that center is less than or equal to so the distance of our point to that center is less than or equal to the radius. If that's true, we add 1 disk because it lies inside that disk. If num disks is greater than best disks, then best disks equals num disks and best P equals P. Alright. Print P. I want to see the point and the number of disks. Best disks and best P. So apparently this point here, 541, intersects with 788 disks. Okay. We don't need to keep printing this. Alright, that's a start. Can we push this, reduce the scale a bit? How far can we go? So we were saying 1,000,000 seems to be takes too long. Try it. But dividing by 10 million really kind of smooths things out too much, so that's kind of a problem. So if scale was 1, then we would have the absolute correct answer, except it might not be because of that weird intersection thing, but... You can make the scale smaller only for the candidates. What do you mean? This takes too long. Oh, stop. So we divide it by... Once you have the suspicious ones, use the original coordinates there, discarding the rest. Mean. So get rid of all the disks that it doesn't lie in. Maybe I'm misunderstanding what you did. All I've done is scaled everything, every number, down by this factor. Try pulling that up a bit. I'm trying to make this scale as small as possible, but still have it actually finish. And then we've got a potential candidate for being near the correct answer. So then we can go back to the original disks and try and use that. Alright, so we've got way more candidates this time. Okay. What's a different completely different location now? 1093. 1093, okay. Maybe I should round instead of round down. Maybe I should round to the nearest. How do I change that? So we want Python want to round yeah, just do that. This will give us better accuracy, I think. Okay, so we're rounding to the nearest integer. Got more boundary points. I was probably missing out a few because of the rounding. (883 1094), same place. Okay, so it's saying almost all the disks intersect on that point. That could be close to the right answer then. So now we want to scale back up. So we're going to say, so it's candidate P equals, let's just take this. So Did I disconnect? Hang on. What's happened here? Why is it not connecting again? Chat's working. Alright, let me just wait for it to connect while I'm thinking. Okay. We should be back. So candidate P equals that times 10, that times 9, that times 4. Alright, so now I'll just kind of comment out all this stuff we did. Okay, so all of this, you can now turn that off. Go back to the original list. Scale equals 1, let's say. Just make sure this is okay. All right. Now we've got a candidate point. Let's count how many disks it lies in. So num disks equals this. Print num disks. 794. Okay. Still feels like a long shot, but okay, but that's promising. We've now have something. What do we do with that now? We need to move that was a boundary point. We need to find the boundary point which is closest to origin, so we might need to push towards the origin. So just for each so let's keep trying to move towards the origin. One step at a time, just move one place until we can no longer get any closer. So what do I mean? So let's say while true. Okay, so location equals start here. While true, we want to look for new this is it's a positive number, so we can hard code this to be subtracting 1. Okay. For delta in -1, 0, 0, either we go one step that way, one step that way. New location equals, it's going to be lock. I should have written some vector methods to instead of doing this all the time. Lock 0 plus delta 0 lock. Damn it. Sometimes the IDE just does things that it thinks it's being helpful, but it's not. New location is that. Now we compute this for that new location. So new num disks equals that. If new num disks is greater or equal to num disks, then we replace lock equals new lock and num disks equals new num disks. Num disks is unlikely to increase because we think we found the best place, but if it does, then we're one step closer to the answer. So yeah, we need to update that as well. Else break. That means if we do this and we find that there's no delta, that means we've basically found the best location. So print lock. Wait, no, what? Shortest Manhattan distance we want. Okay, so print lock and just say dist of lock with 0, 0. It's just the sum of its. All right, go. It's claiming that is the Also, did num disks change? No, it didn't, but we pushed a little bit closer to the origin. Oh man. Should we go for it? I mean, it seems plausible because that's like 4/5 of all the disks intersect on that point. So unless there's some smaller disks intersecting, could actually be. Nope, it's too high. So there's a closer location. So I think we do need to see a picture of this. What does I could use map.lib or something. I think you can plot 3D stuff, can't you? So this is 794 discs. So how are we missing? I think it was just rounding it. Errors mean you don't always get. Also, yeah, this boundary process is problematic because it doesn't quite work. It's not. Oh man. Is this the end for Hero Extra? Well, I've had problems in the past where it took me many hours to solve them. So I might have to leave it for another stream, but I think if there's some quick fix I can do here, because it seems like we've got something good here, but it... That other thing I was doing with the corners, try that. Let's just try it and see if we can get a higher discount than this. So, just put that away for now. Well, okay, just leave that there. This is not harming us, but, corners. Okay, so corners. Define get. Corners. So it's going to be, yeah, similar to what we did with we can copy this and modify it. It's not going to be as complex, so get, oh yeah, get corners I, so pause R, so we just want, instead of range, we actually want K in, okay, for delta in, so it's going to be either R 0 0 0 R 0 0 0 R, for sine in -1, 1. Yield, we want, so it's going to be pos 0 plus sine times delta 0. There's 1, 1, 2, 2. That's corners. So there's 6 corners for each of those. So then if we repeat this process up here, in fact, we could just reuse the old code. Move this up. So get corners. So just do this, but instead of corners, we're using boundaries. So that means we can use the non-scaled star. Okay, so check that out. So corners equals set get corners I, and then everything is as normal. If that's candidates, I for Jane. We don't need this. Candidates equals put this up here. So just say for I in range n candidates wow. Let's see what it does. 6,000. Oh? Okay, we've improved the number of disks using this corners approach. This worked better than the scaling. I suppose there's just a lot of rounding issues when you're scaling. Got 882. Hang on, what are we printing it? So the final thing we found was 882. Just try that. You didn't do the scaling the way I meant, I think. I don't know. All I did was scale the whole thing. Basically just rounding every space of a size 1,000,000 to 1 point. So just zooming out of the grid, that's what I did. I'm not sure how else you mean scaling. Okay, it's not the right answer. I wasn't really expecting it to be, but we did find a better coordinate, a better intersect. 882. Meant like scale to 1,000,000th. Well, then find a suspicious sector and using only that sector. What does scale to 1,000,000th mean? You mean divide all the numbers by 1,000,000? Okay. I did divide all the numbers by million, so then find a suspicious sector. Sector as in, like, define a boundary around it, and then kind of restrict to that boundary. Yeah, you could do that. I'm just worried that, well, that there could be several suspicious sectors and you're not sure which one would lead to the right one, but... Hmm. 882. This is very interesting. Okay, so it seems the corner is not actually inside the intersection set, but... Wait, just to be clear, am I... Shortest Manhattan distance between any of those points? Ah, yeah. Shortest Manhattan distance between any of those points is 0, 0, 0. (882). So that's basically 90% of the disks all intersect on this point here. Somewhere we can do better. Okay, let's say... No, I'm not sure. So it's probably like if we were to walk a bit, we would lose a couple of discs, but we might gain more discs. So you can't really make... I can't make any assumptions here. Can't use a hex tree. So maybe we can go somewhere in between. So I just use the corners. And and if you use the full boundary, clearly that's too much. And if you use just the corners, that's too few. But we could go in between. You could do the boundary, but you only take a sample of points around the boundary. So that would be in between these two, and then you can scale it until you find a good point. So I don't know, try something like that. So let's reuse our boundary, but let's say scale equals... What am I doing with the scale, though? I'm saying... step equals that. Oh, what are we trying to do? What, subdivide each... First 1, 2... I'm not sure what you are referring to. Oh, you mean how to sample points from this boundary? What am I actually trying to do? I'm trying to subdivide each base into points. Ah, okay. So the step size, we want subdivision. Let's say we subdivide into 10. All right. So for each of these ranges, instead of trying K from 0 up to R, I want to divide the space into 10, but I also want to include R. Actually, we don't have to. Okay, let's do this. 0, R plus 1. Hang on, what am I trying to do here? No, because... Hang on, let me think. Yeah, okay. So we go 0, R plus 1, and then it will be R divided by subdiv. So we go from 0 up to R, but by small amounts. So if I do subdiv 10, then it will be like 10 or 11 points there. 10 or 11 here, 10 or 11 here, so we get 1,000 points instead of the full boundary, which is way more, but more than the corners. Okay, let's try that. So candidates equals set I in range. Oh, we got to do this thing again, so we got to... Don't want that. Okay, so we want boundaries equals set of get boundary I or I in range n. So that's all the boundaries, and then this should just work. Let's just start printing useful stuff now. Why is my computer slowing down? I'm not running anything, am I? Is there some process that's been left hanging here? Whatever. Okay, so I'm subdividing into 10. So let's just try that then. Otherwise we can subdivide further. So the smaller the subdiv number, if it was 1, then we just get the corners. This is too slow. Let's try making. Let's just subdivide it into like 4 or something. Is that, will that even that run? Oh! I forgot to do it for Jay and okay. Is this correct? Okay, I don't know. It'll give us points that are on the boundary, so num candidate 0. What did I do wrong? Boundaries I and boundaries J. Try printing boundaries. That looks like boundaries. Oh no, they're not gonna, of course they're not gonna intersect. Okay, no, we're not trying to intersect them. Stop trying to intersect them. We just want to use them as candidates. The point was to use them. Stop. Okay. Whoops. Yeah, don't do this. Or this. Or this. Just do this. And use get boundary. Okay. So we've got 78,000 candidates when we subdivide by factor 4. Uh, 891? What did I have before? Well, oh, that's the same, isn't it? No. Slightly better. 891. No, didn't I? What did I have before? I can check by switching back to corners. Alright, let's just try this number. It's too high. If I go back to using corners... I think I had a better result with corners, which doesn't make sense. I don't think this boundary is, maybe it's slightly wrong. So 891. 882. We did actually improve. Using the boundary instead of the corners. Okay. So we're getting better. So the bigger this number, the more points we put on the boundary. So if I change it to 8, is this going to be too much now? Oh, that is way too much, isn't it? 200, almost 300,000. Well, once we have those candidates, you just have to check against all the disks. So in theory, if you keep increasing this subdiv, you would get the correct answer eventually because you're using all the boundary points. It would be exactly correct if subdiv was infinity, basically. 909! Got to 909. But the fact that we keep increasing feels like we're still way off. They're not even telling us now whether it's too high or too low. Okay, well, we got to 909. Can I push it further? I don't know. I think maybe I should carry on next stream with this. This is, I need to put in some thinking time tonight while I'm in bed. How long have I been on this? Only 2 hours? No, the stream disconnected, didn't it? So a bit longer. No, it has only been 2 hours. I've been recording. It felt like way longer than 2 hours. We could push this to 12, but then it's gonna start. We're gonna. How much? So once we get this num candidates, for each candidate we're checking all disks. So basically multiply by 1,000. Okay, just try pushing the subdiv a bit higher. Let's go for 12. So now it's almost 1 million, so we're basically doing 1 billion comparisons. Is there a way we can improve this comparisons thing? So, given a point. I think I should have just gone for the textbook approach and calculate. Use this what is called, it's called like the trapezium map. So you take you insert your convex spaces into the grid. So we've got these big diamonds. Each time you have two which intersect, you destroy them and replace them with a bunch of smaller convex shapes. So there's two which are not intersecting, and then there's one which is basically the intersection, which is also a convex space. So you're storing, so if two of them intersect, instead of storing those two trapeziums, you store three shapes. One which is the intersection, and two which are the kind of the leftovers. And if you do that, then each time you introduce a new shape to the mix, you only Up to, I don't know, still a bit. Let's see if this completes. $907. Still improving. Are we? Let's try this then. $49 seconds left. So should I submit him now? 2 seconds. Oh man. It's not correct, but 907. Let's make a note of this. Okay, I think I should just think about this offline. I don't want to just be sitting here thinking about it on stream. But looks like we're getting close. I'm not sure what measure I'm going off there, but it doesn't necessarily mean that the correct answer is near this point. But yeah, subdividing the boundary does certainly help. How big are these boundaries? Millions. So for one disc, no, but the boundary is going to be like the square of that. You could project into 2D. You could squash everything to 2D. Because all those intersections would still be intersections in the 2D plane. just that you create new intersections which weren't intersections before. That's the problem. But that could, you do that, you could give you an idea where to go. Oh man. So the expensive process is really for each of these candidates. The bottleneck is this basically. Is there a way I can cut this down? Did you finish Mario RPG? No, I've got 2 stars so far. Out of 7, I guess. So, I think there's still a lot more to come. I got Super Mario Kart, but at least I beat Pepsi Man yesterday. That was a nice win. I got 4.5 hours. I beat it in 4.5 hours, I think. So that puts me probably not high enough to get points, but it's nice not to be last for a change. Submissions, let's see. Check subs. Pepsi Man. So I beat 16-bit, Steven's Rocket, Kylorian. It's hard to use this, but the people who beat it in like 1.5 hours often, so I guess yeah, I only beat 3 people. A lot of people ahead of me. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 12 people above me. Okay. I am getting kind of bored of this. I need to think about this offline, and I'm tempted just to push it a little bit further. Maybe go for 16 instead, or 15. Let's see how many candidates there are. Almost 1 million. So we're doing 1 billion comparisons here. I want to stream the Tomb Raider remasters in February, so probably won't participate this wheel. Remasters? Which remasters? You mean the reboots? Or is there a remaster for Tomb Raider 1? They're coming out in February for 1, 2, and 3. Oh, really? Are they on Steam? Tomb Raider 1, 2, 3 remastered. Cool. That's nice. Because the Steam version of Tomb Raider 1 does also work fine, but yeah, it's nice that they're... I don't know about 2 and 3, but yeah. Alright, oh, I've started it running. Let's see if it actually finishes, but it probably won't. Well, it probably will. I've only gone from 700 to 900,000. Okay, it'll just take a while. We have the expansions too, which aren't available on Steam. There were expansions for what, Tomb Raider 3? Tomb Raider 3 The Lost Artifact? Oh, there were expansion games for the first 2 games as well. Interesting. I didn't know about that. Unfinished business. Unfinished business. Was it on PS1? And like, I guess, why would it be called an expansion? Wouldn't it just be a separate game? Oh, story expansion, I suppose. Yeah, probably PC only. Oh, then yeah, that makes sense. Yeah, the wheel is PS1 only for Tomb Raider, which is a shame because I've got it on PC. I bought the Tomb Raider collection. I don't really play them because I'm not actually that interested in Tomb Raider, but if it comes up on the wheel, I'll be happy to play it, but I can't use the version I paid for. I gotta use PS1 emulator. I mean, the PC version is pretty much the same, isn't it? So I don't think there was any reason to restrict it. Or maybe the PC version is just better graphics and stuff, and that might give PC players an advantage. Oh, the draw distance is probably better. Not that draw distance matters too much in Tomb Raider, but I don't know. It's a 909. Isn't that what I had before? Huh? I didn't even show it on stream because I didn't think it was going to work. It was one less than what I had before. That big number. It was this, but hang on, let me Control Z to make sure. Yeah, it was. It was just 12 at the end instead of 13. But why didn't my walking algorithm detect that? Because I should have stepped closer to the origin. Why wouldn't it detect that? That's weird. Okay. I don't know what happened there. I guess I'm not even that interested anymore. 25, 24 and 25 are usually easier, right? Usually, I think there have been a couple of times where the Christmas Day one was actually kind of hard, but at least it's only part one usually. But there have... Oh, so there was one that was, I remember, quite hard. Was it 2022? What is Christmas Day? Yeah, this one was last year's. And this actually was quite conceptually quite difficult. It was the snafu one, so it uses some code. It basically has created this code, but it's very irregular code, and it's quite hard to work out how to convert it to and from decimal. And I found it tricky, but I think a lot of people will find it more hard than I found it, because it's kind of mathematics oriented, so people who are not as good with maths would struggle a bit more than I did, I think. It's an interesting problem. It's quite original, quite clever, but it's tricky to wrap your head around at first. Basically, you're trying to... You're just trying to decode and encoding using this encoding scheme. So that was hard, but oh, they're ordered the other way around. This one. The other one I did was another encryption one. I guess encryption is common for the Christmas Day. Oh, it is actually public-private key encryption. I can't remember if this one was hard. I don't think it was that hard, but it is quite mathematically oriented. Do I take a sneak peek at 2021? Are we allowed to? I mean, am I allowing myself to? Okay, go on, just for a second. Oh, this one looks like some sort of map, some sort of game, moving stuff around. Okay, it's a simulation. Wow, okay. See, if I hadn't tried running that again, I would have probably just started with some completely different approach next stream and maybe not even get anywhere, so who knows how many more hours I would have been on it for. Okay, so yeah, that's good. Just 2 days left. I could even maybe do both days tomorrow. We'll see. Alright. I'm gonna have dinner and then maybe play some game. Reward myself with some... All the games I'm playing right now require thinking, though. I want something which I don't have to think for. Halo 3 is on the horizon, but I need to re-download the Master Chief Collection. Because I just finished reading the book, and now it's made me keen to play Halo 3. Like Sonic CD, no, that does actually make me have to think a lot. Oh man, I hated Sonic so much. Everything that was wrong with Sonic was actually corrected in Pepsi Man. I think Pepsi Man was actually just way better than Sonic in every way. Like, I was complaining about how, you know, you gotta learn through dying in Sonic. You don't really have to do that in Pepsi Man. You can see a situation for the level for the first time in Pepsi Man and actually get through it on your skill alone. So you don't have to learn through dying, which I hate doing in games, because that's just like that was designed to eat your quarters. It was a money-making device. It was put there so that people would pay more quarters to because they kept dying. We don't live in those times anymore. Yeah. But Pepsi Man also had good draw distance. You could actually see where you're running. You're not punished for going fast. That was one of the worst things about Sonic. If you got okay, I'm starting to rant about Sonic. We've had this rant before, and this is a programming stream, so whoever's watching this YouTube video is pretty confused as to what we're talking about. I'll just leave it there. Yeah, so that was problem 23. Might be able to do another coding stream tomorrow. We'll see. All right. Thanks for watching. See you next time.